Welcome, everybody. My name is Jancy Diaz-Mercado. I'm an assistant professor at the University of Maryland, and I would like to welcome you to today's Future Leaders in Robotics and AI, Celebrating Diversity and Innovation Seminar, sponsored by the Microsoft DC Metro Engineering site. I would like to encourage everybody in the attendee list to visit our website for previous presentations from future leaders, as well as information on how you would go about making nominations for future instances. It is my distinct pleasure to introduce our first speaker today, Krishna Murthy. He is a postdoc at MIT with Josh Tenenbaum and Antonio Torralba. His research focuses on building multisensory world models to help embodied agents perceive, reason about, and act in the world around them. He has organized multiple workshops on themes spanning differentiable programming, physical reasoning, 3D vision and graphics, and ML research dissemination. His research has been recognized with graduate fellowships awards from NVIDIA and Google, a Best Award, Paper Award on Robotics and Automation Letters, and the induction into the RSS Pioneers cohort. Without further ado, Krishna, please take it away.
Thanks. Thanks for the gracious introduction. Let's see if screen share. What's up? All right. So yeah, I'm going to be talking about structured neural models for robots. And I work on building robots that can understand the world around them. So imagine asking a robot in this environment to help you find your keys or like find shoes that match an outfit. These are tasks that we think of as extremely simple, but these are very, very challenging even with the best AI systems we have out there today. So if you think about all the capabilities that a system would need to solve these kinds of tasks, the most fundamental capability is certainly to just kind of know what is where in the world, and then you need to be able to interpret the context in which tasks are provided to you, such as like finding, for example, the dress in question for which you need to find these matching shoes, and then you are able to plan actions to achieve these goals. So if you think about how humans do this all the time, there's many cognitive theories that support the idea that humans build these mental world models. So these are basically internal representations that we build that can simulate and reason about the external world. So these are basically built up on our prior beliefs, and you can update them as you get more and more evidence. And these are ultimately what drive your rational prediction or decision making towards achieving your goals. But so for an example, just consider the amount of information you can derive from watching these sequence of images. You can infer the geometric structure of the world. You're also able to infer that the world is composed of a collection of meaningful objects. So in addition to just being able to impute missing sense data, you can also predict what could happen. So if you were to turn a little bit to your right, what would you expect to see? And you can use these to plan actions to achieve your goals. So if you need to get to the door, how do you get there? And the most fascinating aspect for me is that you can query these models and perform a lot of hypothetical and counterfactual reasoning, such as why did this happen? How could I make something else happen? And ultimately, you can update the model whenever real world contradicts or observations contradict your prior beliefs. So these are, of course, central to human intelligence. And this is what a lot of my work takes inspiration from. If you look at modern AI techniques, so all of these successes we've had in image, text, speech, and video processing, at the heart of all of it is this notion of just scale, bigger data, bigger models, and trained with bigger amounts of compute. So across any of these approaches, we will take like a state-of-the-art architecture or model to look something like this. These are just large transformer architectures trained on large data sets. And there's lots of evidence to support that scale is kind of necessary to all of these behaviors we see. But I tend to think that scale is not sufficient. So if you think about all of the applications with scaling has been successful, you see like all of these domains for which abundant amounts of data is available on the internet, billions or trillions of data points. But you start going towards domains that are closer and closer to the real world. Think about 3D content for one. So a lot of the 3D content you see on the internet is kind of static objects or static scenes, but there's 5 or 6 fewer orders of magnitude when you already come to 3D content. And think about data that's more relevant to robotics that includes perception and control inputs, and you lose an order of magnitude more So as you get closer and closer to the real world, there's this issue of the domain becomes more and more complex while relevant to robotics, but you are losing out on the amounts of information available to just naively scale these approaches. So what's missing? And in my research, the idea I tend to apply is the notion of structure, things that we know about the real world that are generally true, and structure that can help you learn faster from less data. And so overall, my research vision is basically to develop computational world models that leverage our structural priors. And there's many, many ways in which people define world models. And here's my definition, just based on the cognitive inspirations about. So I like building computation models, and these basically integrate our prior knowledge with sense data that we get on the fly. And these can help us simulate, predict, and understand, both in terms of structure as well as dynamics of the external world. And these can be fully handcrafted, fully learned anywhere in between. But for me, the crucial aspects are these support queryability. These can be answered to used to answer a lot of where, how, and why kind of questions. And in my work, the kinds of structure I've leveraged to build these models is structures that we know are true sort of universally, geometry, physics, graphics, and so on. So overall, there's like three main thrust areas in which I work on. There's spatial and semantic understanding, or I like to use the motto, knowing what is where, or physical understanding, or predicting what might happen, and multimodal understanding, which is basically how do you integrate knowledge from all of these sources to build richer representations of the world. So for today's talk, I'm going to focus on some of our recent results on the multimodal understanding front. And over here, our research thrust has largely been, there's a lot of internet scale data, like models trained on other modalities. How do we best make use of all of these pieces of information and bake in the right kind of structure so that you can upgrade these for 3D understanding? So imagine, imagine just asking your robot to find something to wear to a space-themed party, and then it finds this T-shirt that says NASA written on it, like asking your robot to get something healthy to eat, and it picks up a mango, or like just someone, you hear a sound corresponding to someone knocking on a door, and then you ask, where's the sound coming from, and you locate the door in the scene. And these are not really just didactic examples. These are like application domains for which we've built models over the last year and a half, and these have been deployed on real-world robots. So let's look at how we do this. So there's a lot of background work and 3D spatial perception. You build 3D maps of the environment. And typically in robotics, there's been lots of approaches that try and build object-centric maps, detecting objects you have prior 3D models for, or there's work that tries to lift semantic segmentations to 3D. So you have point cloud reconstructions where every point is labeled with some notion of what that is. Is it a bed? Is it wall, ceiling, floor? And you also have hierarchical representations that break down an environment into objects, agents, places, rooms, buildings. And some characteristics we have of all of these kinds of work is that they're close set, meaning all of the objects and classes of interest are known a priori at train time. And then these are unimodal. You can query them using some kind of a class ID or label, which you need to know again beforehand. And these also tend to be very sensor specific. But then if you look at what's happening in computer vision and language, there's new kinds of solutions. So as opposed to training domain-specific models, you kind of have these models that are general purpose and very rich. So there's vision models that are pre-trained on hundreds of millions of images that can extract useful features. And you can just train a linear classifier, something as simple as that on top for adapting it to new tasks. Or there's other techniques to align data from different modalities together. Techniques like CLIP, for example. You have a database of, let's say, 1 billion images, each image with its corresponding text description. You can take descriptions, so you encode the text using a text encoder, you encode the image using an image encoder, and then you embed them. You train them in such a way that you pull all the corresponding image text pairs together and you push everything else apart. And this gives you general purpose representations that can be used you can construct classifiers, for example, out of this very easily. So if you want a plane versus car versus dog versus bird classifier, you just get text descriptions of each of these. And when you have an image, you encode it and you compute a cosine similarity, which tells you what label of these text categories this belong to. So this seems a very promising and powerful idea in terms of just vision language alignment. Can we, and this is not just limited to vision language, people have also aligned all sorts of other modalities such as audio with this. So can we think of bringing this to the fore in terms of 3D mapping? So this is what we do in one of our recent, not so recent paper called Concept Fusion. And over here, the idea is, can we augment 3D maps of the world, 3D point cloud maps are what we talk about in this work? Can we augment them with queryable features, features queryable with multiple kinds of modalities? And again, we do not want to train new models for this from scratch because we have such a large collection of very capable models. Can we just take them off the shelf and lift them to 3D? We are just the nice rules of projective geometry and simultaneous localization mapping we've been studying for a while. But then the challenge is, how do you extract these multimodal per pixel features? Because if you think about the clip description I showed earlier, clip extracts, it takes in an image and converts it into a single description or a single embedding vector. So there's prior work that tries to do something like this, where you try to extract per pixel dense features from clip. And this involves some form of fine tuning. So you take a clip backbone and then you fine tune it on top using a smaller held out fine tuning data set, which has all the substrate to support dense prediction. But then you need to kind of retrain each time you want to align this to a new clip model. But not just this, but the bigger issue at hand is that you tend to forget concepts that are not present during the fine tuning data set. So if you think about concepts like yogurt or Diet Coke or Lysol, which the clip backbone knows, but the dense prediction fine-tuning phase just does not include enough data about, these are kind of quickly forgotten. So we come up with a way of computing features that does not involve any retraining of the backbone. So you have an image. We use class-agnostic instant segmentation approaches, like the segment anything approach, to decompose this image into a set of masks or set of informative semantic regions. And using a frozen clip encoder, you compute various kinds of features at various levels of granularity. So you compute a feature for the entire image, and then you compute feature descriptors, like clip feature descriptors for each of the detected segments. And now we take all of these and compute like an all pairs cosine similarity. And this gives us information about, so this local region here, if we compute the cosine similarity with respect to the whole image, we get a score, a single scalar score that says, how relevant is this small region to the overall identity of the image? So you can assume things like a bed and a bedroom getting a very high cosine similarity to full image of the bedroom with something else, not so much. So this way, you can extract pixel-aligned or almost pixel-aligned features, which allow you to do interesting things. So you have this image of teddy bear here. You can type in a text query that says teddy bear, and you can now search for all the pixels in the image that maximally respond to this query, and all the pixels in green maximally respond to this query. Or you can extend this to multi-class classification, where you have a set of concepts. So we've already moved from like 1D to sort of 2D segmentation style tasks. Can we now do something better, like upgrade this to 3D? And well, before that, just a quick revisit to the example that I showed before. Like, since we're not fine-tuning anything, there's very less risk of forgetting. And we indeed see that our model, without any fine-tuning, can get all of these masks very accurately. And it can give a very sharp contrast between the rest of the concepts and concept of interest. So just to quickly recap, we compute these pixel-aligned features, and then we lift these to 3D via SLAM. And these representations are much better because we fuse them across multiple views as opposed to just looking at a single image as in the previous case. There may be some images in which some objects are small or just occluded. So fusing this via SLAM ensures that you get good representations that fuse, that eliminate noise. and pull in all of the information you have across views. And again, you don't need any additional training or fine tuning, which is always helpful because the rate of development there is in modern AI, you just want to very quickly adapt as new models are released. So one of the things we observed here was as you tend to cluster, so you take the 3D map and then you just apply k-means clustering. As we go from left to right, you have increasing values of k, and the maps naturally cluster into meaningful objects. You can now do things like, for example, you take this map and you search for the query, I need a place to watch TV. And this is encoded via the clip text encoder into text embedding. And you search for this over the entire map. And these are the areas with the maximum cosine similarity. You can also do things like play a ceramic clicking audio and then say which object in the scene produces the sound. Or you can just get an image of a random cabinet from the internet and then say find all similarly themed concepts in the scene. You find other cabinets in the scene. Or you can just click on a single point and say, like, get me all other points that correspond to this clicked object. And this can be very useful if you want to, for example, annotate objects. You just click on one and you get the entire object out. So we applied this in a number of scenarios. For example, for here, we search for the term roundabout and we are localizing the near roundabout. And think of this as a city block size scan. And we plan a trajectory and autonomously navigate to this roundabout. Hold this play for a bit. All right, and you can also do things like instruct the robot in language, like move Baymax so right. It understands the notion of the Disney character Baymax. And since we don't require any training, you can also do things like align to other fancy clip backbones, like a multilingual clip, do the same query in multiple languages. But again, if you look at all of these maps have millions of points, and you have a clip descriptor per 3 point. Think of 1,000 dimensions or so per descriptor, and floating point or half precision. This very quickly begins to take up a lot of space, or memory becomes a crunch. So to circumvent memory issues and also to enhance this approach, we developed this a whole new mapping pipeline on top of concept fusion, which we call concept graphs, where the idea is you take in these images, you get masks or object detections from open vocabulary detectors, and then you build these maps that have objects in them that are factorized into objects. You can send these objects, you can extract linguistic descriptions of these objects, and you now have a scene description that you can feed to a language module. And that allows for more abstract queries, such as asking what goes well with the Ronald McDonald outfit. So for here, the robot finds shoes in the scene, red and white sneakers, and it says the Ronald McDonald outfit is like a red and yellow outfit, so these red and white sneakers will go with it. Or you can merge queries that involve both text and visual context, where you just show a picture of Michael Jordan and say something this person would play with, and you find basketball in the scene. And in the few months that this framework has been out, it's already being used by a number of others, including some of which are from our group and other collaborators externally. So a very quick set of takeaways for this part of the talk is like using open vocabulary structured scene representations allows you to do a lot more than just static or closed set representations allow you. But the key here is we are retaining all the algorithmic scaffolding or symbolic structures like scene graphs or 3D representations that allow us to very quickly scale, both in terms of performance and also in terms of just production time as more and more of these models are developed or released over time. So again, with this, since we're almost out of time, I'll also try and come up give you a quick picture of what I think the future vision for most models like this are. So we have all of these kinds of multimodal, very capable models, and why do we even need structure? So when I think of how robot learning would eventually scale, so we discussed the scaling approach initially, but then how do we scale robot learning? One way I think it's definitely very promising is what I call the 80-20 approach, where we do 20% of the work. So as opposed to building robots that are like perfect from the get-go, just build robots that can provide new pieces of information that can be taught new knowledge very, very quickly. And this becomes a virtuous cycle where you kind of have, you can deploy robots out, they collect more data for you, and they become more capable. You can deploy them across more applications, and the cycle goes on. But to establish in the first place, you kind of need to build some structural models. So the question really is what is built in versus what's learned, which is where like structural representations will come in. So, and I'm not saying this is just the work of a single researcher agenda. There's lots of other domains of robotics that kind of need progress. We need to figure out planning, bi-level planning in really high state spaces. How do we learn new skills quickly? And also how do you deploy all of these large models and robots very effectively? So with that, I will just stop here, thank all of my collaborators, and then open the floor up to questions.
So I know it's a little jarring with nobody here, but I'm going to clap on behalf of the entire attendee list. I'm sure they're all clapping themselves. Thank you for that wonderful presentation. Do we have any questions from the audience? You can go ahead and post your questions using the Q&A feature. And I'll give you a moment to do that. I do have a question. So some of the semantic information that you're describing here, that comes from these already kind of built LLMs. Is that correct? Like the ability to understand, what it means to sit, right? When I say, find me somewhere to sit. That's not something you're necessarily training. You're kind of leveraging the information that's out there, if I understood correctly.
That is true. So I guess. So we now have this all of these very powerful and capable models. So if you need something very, very abstract, it does seem like that's some of the best ways to leverage them. But again, these models are not fail-safe. So the example you gave is actually a good segue. Like we can talk about a place to sit. So if we have models like Flip that came out like 2 or 3 years ago, they would just say, well, there's a chair, and in all of the data set I've seen so far, I kind of associate or correlates well with the word sit. So I would just assign a high similarity to any chair, regardless of whether it's empty or not, or whether it's like a tiny miniature chair versus like a full-size chair, or if the chair has like a pile of clothes on it, I'd still say it's a place to sit. But so newer vision language models we have are becoming more capable and kind of trying to reason about the fact that, well, you can probably sit in this chair, but you'll have to take the clothes out and put somewhere else. But there's a miniature chair, so there's not something you can sit on. Which is also why necessitated this like shift from the concept fusion style approach I described to the future concept graphs pipeline described later in the talk.
That's really cool. And I'm almost wondering now, how do we expand these models to include other, perhaps domain-specific knowledge, right? So, we're dealing with robots, right? And there's a number of features that we could ask robots, like, oh, go fetch me something, for example. But we potentially, in the design of these robots that we're going to deploy so that we learn something so we can deploy more robots, there are things that we want to explore that are specific, right, to, robotics. So do you envision that we're going to be doing like, planning or learning how to plan by telling robots to figure it out? And how do we get those models?
Yeah, I guess one very interesting way to think about like the next way of learning algorithms is where we can instruct these algorithms either via simple mechanisms like just by language, or we are able to like teach these models new pieces of information quickly. For example, you can very quickly show robots how to imitate or like how to pick up this particular object. Like we always have that one door in our house that has to open very differently. Like you always have to be very careful when opening that, or there's always objects like that which need to be dealt with care. So I would really like for these algorithms in future to like have actions as like first class citizens in there. Like you need to be able to, for example, instruct when something goes wrong. Like you can just say, well, you know what, I just prefer this area of my workspace to be very, very clear of anything else. It's better you don't encourage in here. So like specifying preferences could be one example where it's not directly related to actions, but it could impact how the robot thinks about, like goes about planning its future tasks. And then you can also think about integrating some newer, there's lots of advances in like behavioral cloning. It's just started to work so well over the last few years. So I wonder if we could integrate some of those into these three scene representations. Like for now, these representations largely perceptual, but they need to be tied to affordances or actions for this to actually work in scale.
Yeah. Yeah, or it's perhaps some physics-based intuition as well, right? And then maybe robots can kind of figure it out on their own. And then I don't know what we're gonna do. We're gonna do something else, I guess, at that point. Because the robots
For sure, yeah. I did not get into all the physical understanding segment of my talk again, since this is a 20-minute talk, but I'm all for that. Like, we need to be able to understand physical properties of objects, at least intuitively. They need not be very perfect. Like, you probably don't need the mass friction coefficient and restitution for every single object in the world, but you need at least cause and effect style relationship. Things like if I flick the switch, the oven will turn on and the food will get warm, without actually understanding, well, how does the convection oven even work?
Excellent. So we do have a question from Tarun Putambetil. I apologize if I butchered that. The question is there any elements of reinforcement learning with human in the loop involved in this project?
Okay, yeah, so not in this work, but in general, I tend to think of reinforcement learning and sort of the symbolic structures or approaches I describe as very much geared towards the same objective. And I think it's best to have both. I go back to Dan Kahneman's fast and slow style example, where I think of reinforcement learning is essential to get to the fast mode. Like, symbolic approach, while it's verifiable and it's good, it can also sometimes tend to be slow. So it would be good to think about, can we have both of these modes and can seamlessly transition from one mode to another? So think of driving a car. You've learned to drive a car for many years, but then when you're in, this is again from the Kahneman book, like when you are in a new area, you're an expert driver or you're driving a storm, you tend to go back to like looking and thinking into every single action very, very carefully. So I'd like to have this kind of seamless switch between both these kinds of modes. So while these two goals may seem sort of different, to me, they are like very much integrated.
Excellent. We do have time for perhaps one more question if the audience has one.
I have a question. Hi. Is it okay if I speak? I just don't think I can type it very quickly.
All right.
Go for it.
So you said that you were interested in switching between these modes. Do you have any like leads? Just to follow up on your most recent statement, like that book I think is really interesting. Actually, in my talk, I might reference it as well. Yeah, I'm just wondering if you have any like ideas for how you might like build a system that uses both, or how you might switch or like think about their interface or stuff like that.
Yeah, I tend to think of, or this is again, it's a little bit hand wavy, but the way I think of it is you have structured models that can essentially serve as your scaffold, or that's how you start out. Something is built in. So you use these models to build policies or like behaviors over time. And these behaviors can be internalized or like offloaded or used into learning pipelines. Could be imitation, could be reinforcement, could be combinations of both. But over time, you just internalize it with any other form of structure. You can think of experience like replay or wake sleep. But then over time, then you build these behaviors and you kind of seamlessly switch into more of RL. You can use, so for all of this to work, we need some measure of task success or uncertainty in our representation. So I guess that could be like the guiding signal between whether we're confident just switching out to a fully learned behavior versus a fully structured one.
Great. Well, I mean, thank you so much again. We're going to thank the speaker for that wonderful presentation.